Alright, today we're going to cover 1.6 descriptive modeling and accuracy. So it says I can use quantities for the purpose of descriptive modeling and report solutions with an appropriate level of accuracy. So first we're going to focus on the descriptive modeling. So descriptive modeling is a way to mathematically describe real-world situations and the factors that cause them. A metric is a rule for assigning a number to some characteristic or attribute. Metrics can be used to make comparisons. In sports, earned run average is used to compare baseball pitchers, and the quarterback rating compares the performance of football quarterbacks. In banking, a person's debt to income ratio can determine whether the person qualifies for a loan. In a good metric, factors that are important in the situation are considered and included in the metric. For example, the quarterback rating includes measures of passing, running, penalties, and other factors that make a quarterback effective. So we're going to go through some examples. I might skip around so that we don't have to do as many examples. So I might skip the checks. It just depends. So example 1 here. Some universities use a metric called the academic index to qualify high school athletic recruits. A student athlete with a 3.1 GPA receives scores of 610 in reading, 640 in writing, and 700 in math on the SAT. Use the expression to determine whether the student athlete qualifies at a university that requires an academic index of 186 or greater. So here's the formula that they use. So they take 2 times, and then in brackets, they take the reading score plus writing score divided by 2, plus the math score divided by 20. Then they add in the GPA value. So here, we're going to go through and we're going to do that with this example. So we're going to plug things in where they go. So if we look at this, we have that we're going to have our 2 bracket, and then our reading score was 610, plus our writing score, which is 640. That's all divided by 2, plus our math score is 700, and then all of this is divided by 20. Make this brace a little bigger. And then we have plus our GPA value. So the GPA was 3.1, which if we follow in that our table, our value is 68. So then we're going to go through and we're going to go ahead and simplify this. So based off order of operations, the first thing we should do is our parentheses. So we're going to have 2 brace. We would take 610 plus 640, which is 1,250. That's over 2, plus our 700 over 20, plus 68. So we still need to simplify what's in this bracket here. So we take 1,250 divided by 2, which is 625. So we have plus 700 over 20 plus 68. So next we'd go ahead and add those 2 numbers in our fraction there. So we have 1,325 over 20 plus 68. So we divide by that 20. If I do that, I get 66.25 plus 68. If I take 2 times that 66.25, I get 132.5 plus 68. Which if we add those, we get 200.5 200.5. So it says that to qualify for this one, you had to have 186 or higher. So 200.5 is greater than 186, so they would qualify. Okay. So the next page has us wanting to kind of do the same thing. It gives us metrics again, and then this one is about state parks. So like I said, we're going to mainly skip these check questions just to kind of save time. So like if I scroll up, oops, we're going to go ahead and skip this check question right here. So we're going to go ahead and focus on comparing metrics. So here, there's going to be two different methods that you can use to solve this problem. So we're dealing with a child's height. So it says a child's adult height can be predicted using several metrics. Given the height of the mother, father, and their son at 2 years old, use the metrics to predict the son's height as an adult. Okay, so they give us two different methods. So method one, the Gray method, or the Gray method. The Gray method uses the average height of the parents adjusted by the gender of the child. For a boy, the mother's height is multiplied by 13 over 12. For a girl, the father's height is multiplied by 12 over 13. So in this case, we're dealing with a son, so we're going to be multiplying the height of the mother by 13 over 2. So they gave us that little formula down there. So we're going to go ahead and we're going to have to plug in our values where they belong. So we're going to have 13 over 2, or 13 over 12, times the mother's height, which was 65 inches, plus the father's height, which is 72 inches, all divided by 2. So if we multiply 13 over 12 by 65, that is going to get me 70.42 plus 72 over 2. If we add those together, we're going to be taking 142.42 divided by 2, which if we do that, we get 71.21. So that gets us that the height of this child is going to be about 71 inches when they're an adult. Okay. So then we can use the doubling method, which in this case, it should turn out to be about the same. So the doubling method multiplies the height of a child by 2 at a specific age to predict the child's height as an adult. Height at 24 months used for boys, and height at 18 months is used for girls. So 24 months would be 2. Okay, so we're going to use this doubling method. So it says that they are at 35 inches right now as a 2-year-old. So to double, we would take 2 times its current height, which is 35. Well, if I take 2 times 35, that gets me 70. So we'd get 70 inches. So both methods got us about the same answer. It's just going to be determining which method we want to use. But these are two methods that they do use to make these predictions. Okay, so the next problem here talks about banks. So it wants you to go through and find which bank has the mortgage or debt to income ratio to figure out who would get the loan. We're going to go ahead and skip the check, and we're going to go right on to accuracy. Because once again, it's just plugging numbers into a formula and figuring out the metrics. So accuracy, all measurements are approximations. When you measure something, you are limited by measurement tools that you are using. Accuracy is the nearness of the measurement to the true value of the measure. The accuracy needed for baking cookies timing the final seconds of a basketball game, and determining the gold medalist of a 100-meter dash are very different. Whether measurements should be rounded depends on how the measurement will be used and the limitations of the unit in which the measurement is taken. So here, the first one, we have to decide where to round. So it says Damien and two of his friends are taking a road trip. They plan to share the responsibility of driving and will each drive an equal distance. Damien's GPS shows the total distance is 172 miles. Determine the exact distance that each person should drive, then determine a more appropriate driving distance for each person given the limitations of the situation. So we'll go ahead and figure out what each person needs to drive, and then we'll kind of talk about how we should round that and why we should round it the way that we round it. So since it's Damien and his two friends, that means that there are going to be a total of 3 people. Because we have Damien, his 2 friends, I add that together, we get 3. We know the total traveled is 172. So we would take that 172 divided by the 3 people. And if you do that, you get 57.3 repeating. And that would be miles. So that's our exact. So then it wants us to figure out what would be a more appropriate rounding distance. Well, if you think about cars, odometers, and GPSs, they usually just give you, especially when it's a big number like 57, whole numbers. They usually don't get into the 0.9s and stuff like that until they get below 10. So in this case, it would be more appropriate for them to each say that they drive 57 miles each. Because once again, our GPS and our car's odometers don't really say that. So here, we'll go ahead and do this one. So we have that they have saved $400 to spend on a 7-day vacation. He plans to budget his $400 by spending the same amount each day of the vacation. Determine the appropriate amount he should spend each day. So we have $400, and we're doing this for 7 days. So we divide by 7, and that gets me 57.14285714. So that's the exact. Well, money only goes to 2 decimal places, and you can spend a certain amount of change each time, so it would be appropriate to round to the correct cent value. So in this case, the appropriate rounding would be $57.14. So we rounded to the nearest cent for this one because money, it makes sense to go to the cents, especially if you have that money saved up on a card, you can spend that exact amount. Where when you're driving, our GPS doesn't allow for those 0.3 repeating miles, so we want to round it to the 57 that we can see. So we'll go ahead and go to our next problem here. So it's going to be find an appropriate level of accuracy. Or the problem disappeared. There it is. Okay, so in 2012, NASA's space shuttle Endeavour traveled approximately 897 miles from the Kennedy Space Center to Houston, Texas, by a shuttle carrier aircraft. Then it traveled back 1,381 miles to the Los Angeles International Airport. Finally, a truck pulled Endeavour 12 miles through the streets of Los Angeles to the California Science Center. In the shuttle carrier aircraft flew at an average speed of 287 miles per hour, and the truck pulled Endeavour at an average rate of 1.3 miles per hour. Determine the total amount of time it took Endeavour to travel from the Kennedy Space Center to the California Science Center with a reasonable level of accuracy. So, if we think about this, we would want to add how far it traveled while it was in the air. So from Kennedy to Houston, it was carried in an aircraft for 897 miles. Then it was carried in an aircraft also by 1,381 miles. So we're going to go ahead and add the aircraft together. So the total air travel was 2,278. Okay. Now for this, we want to do miles per hour. So we're going to be taking miles divided by our miles per hour, because we want to get just hours. So we'll take how far they traveled divided by their speed, and that will give us how many hours it took them to travel during that. So for the aircraft, they traveled 2,278 miles, and then we are told that its speed was 287 miles per hour. So that will tell us how many hours it was in the aircraft. So then we have to do the same thing for the car. Well, for our car, it only traveled 12 miles, and its speed was 1.3 miles per hour. So we have to divide by 1.3. So if we were to divide those, we're going to get that for the aircraft, it took them about 7.937 hours. Plus, for our car, our truck, it took them about 9.231 hours. So we'd want to add those together, which if we do, we get about 17.168. So an appropriate level of accuracy, when we talk about hours, we usually just say it was about 5 hours, or we say like 5.5. We don't really say 17.168 hours. So we would say that this took about 17 hours. So it's going to be getting as an appropriate measurement as you can, and then thinking about what level of rounding makes the most sense here. So in this one, it makes sense to go to 17 hours than anything else. So for this next one here, we have postage. So it says, a school is hosting a marching band competition and plans to mail postcards, flyers, and large information packets to other schools. The school will mail 150 postcards, which cost 34 cents in postage, and between 75 to 100 flyers, which cost 49 cents in postage. 43 information packets will be mailed. The cost of mailing the information packets varies, but the average is $1.59. Determine the total mailing cost that represents the most reasonable level of accuracy. So, for our postcard in our information packets, we are given an exact number, 150 and 43. For flyers, though, we're given a range. So we're going to calculate with the low range and then calculate with the high range so that we can compare them. So when we're trying to figure out this total cost, for each of these things, we're going to need to take the item times its cost. And then we'll have to add all those up. So for our postcards, we're doing 150 items times its cost, which is going to be 34 cents. Plus, like I said for the flyers, for the first one, I'm going with the low, so 75 times its 49 cents. Plus our 43 information packets, which are $1.59. So if I take 150 times 0.34, that gets me $51. 75 times 0.49 is 36.75. And then 43 times 1.59 is 68.37. So if we add all that up, we get that this is $156.12. So then we're going to do the same thing, but now we're going to do it with 100 flyers to see what the difference between the two is, because we're trying to find the most appropriate rounding situation. So everything else we can just copy down because it stays the same. So this time we're doing 100 times 0.49. So this is still going to be $51 for the first thing, and then it's still going to be the $68.37 for the last thing. If I take 100 times 0.49, that's 49. So if we add this up, we're going to get 168.37. So the total cost would be somewhere between these two. Okay, so the most appropriate level of accuracy to use here would be to say that we're going to spend about $160, because $160 is reasonably between these two values. So it's just, a lot of this is going to be up to interpretation, but it's going to be trying to pick the most accurate representation. So we have two more examples left here. So this next one up here says determine accuracy. So the U.S. Census Bureau website shows a counter that displays the population of the United States on a certain day as 329,158,023. How accurate is the reported population? Explain your reasoning. So they have this little diagram here. So components of population change, that we have one birth every 7 seconds, one death every 13 seconds, one international migrant net every 29 seconds, and then net gain of one person every 11 seconds. So if we think about the United States, there are a lot of people. So there's no way to go and count every person in the United States at a given moment, because we can never get an exact population, because all these deaths and births, they're not happening at a steady rate. They actually vary. This is just an average. So there's no exact way to get how many people in the United States at one moment, because it's constantly changing. It's constantly in flux. So this is not going to be an appropriate way to do this. So it wants us to explain our reasoning, and then that's why it wouldn't work. So instead of it going into that much detail, it should use more of an approximation. So it should say something like this. So it would be more appropriate for the website to report the population as about 329.2 million. Instead of it trying to say an exact amount, it should do a roundabout way of going with its rounding. So like 158,000, that's about 150,000. So we round it up to 200,000 because it is constantly changing. My T didn't cross. So you want to make sure that you're doing stuff that makes sense, to where you're not over or under kind of basing your statistics here. So with this biology one, it wants us to say if this is accurate. So if this is more reasonable to say. So we don't want to go too specific, because we could not be correct. So here it says a Science magazine reported that there are, on average, 37 trillion cells that make up the human body. Select the option that best describes the accuracy of the magazine. So A, the magazine is accurate because scientists can count every cell. B, the magazine is probably accurate because the number is not very specific. C, the magazine is not accurate because there is no way to count all of the cells of a person. Or D, the magazine is not accurate because the number of cells is always changing. So the first one is out, because there's no way that a scientist can sit there and count all these cells, especially because our body is changing, we make new cells and stuff like that. So that would be out. We can't have 37 trillion cells being counted by a scientist. B, because it's not specific. That is reasonable because there's no way for them to actually get into that nitty gritty of counting. So it would be accurate to try and round like that, like we did with the population in that first example. The next one says there's no way to count all those cells. Yes, that is true for a person to just sit there and count all those cells, but we could make an approximation, which is accurate. And then not accurate because it's changing. It's always changing. Like if it changes like very slightly. So that wouldn't make sense to say. So the most reasonable answer to this question is going to be B, that it's not very specific because it's going to be rounding. And rounding is still an approximation, so there's still that level of accuracy when you're rounding. And that will be it for the 1.6 notes.